Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on nuclear energy. Today, you will learn about the energy that is released during nuclear reactions, and you will discover the difference between nuclear fission and nuclear fusion. Let us get started with the lesson. As you have seen, students, there are two basic ways that atoms produce energy. Either they combine with other atoms or they split apart. We sometimes have negative associations with the phrase splitting atoms. It is easy to forget that nuclear fission happens naturally every day. Nuclear fission is a nuclear reaction in which the nucleus of an atom splits into smaller parts, often producing free neutrons and energy in the form of gamma rays. Fission is an exothermic reaction that releases large amounts of energy, both as electromagnetic radiation and as kinetic energy. Fission can occur in two ways. Students, you have already learned about the first way fission occurs. In radioactive decay or spontaneous fission, a nucleus becomes more stable by splitting into two or more parts and emitting particles. As you have learned, radioactive decay is impossible to predict precisely. So, in order for us to use nuclear fission to produce energy in a controlled environment, we must use a method called neutron bombardment or induced fission. Uranium is an element that is constantly undergoing very slow, spontaneous fission. It naturally emits radiation, which makes it a natural choice for induced fission. Substances such as uranium are called nuclear fuels because they undergo fission when they are struck by free neutrons. Students, here we see an example of uranium undergoing induced fission. When it is bombarded by a free neutron, the uranium nucleus splits into two daughter nuclei and releases energy and fast neutrons. These neutron emissions are another reason why uranium is a good choice for induced fission. Can you think of why this might be the case? Please take a few minutes to think about the question and discuss your answer with a classmate.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. With a little thought, I am sure you came up with the correct answer. Every neutron that is emitted through the fission of uranium is capable of triggering another fission event. Here we see a depiction of uranium atoms inside the reactor vessel of a nuclear power plant. As each uranium nuclide is struck by a free neutron, it splits and releases more free neutrons that strike other uranium nuclei. This triggers a chain reaction. When a uranium nuclide fissions, it releases an energy of around 200 mega electron volts. In comparison, most chemical oxidation reactions, such as burning coal, release at most a few electron volts per event. The energy from fission comes from the kinetic energy of the daughter nuclei flying apart and the kinetic energy of the neutrons. It also comes from the emission of electromagnetic radiation, which can be converted to heat. Nuclear fusion reactions have an energy density that is many times greater than even nuclear fission. Nuclear fusion is a nuclear reaction in which two nuclides are fused together to form a new nuclide. Fission releases the energy of the electromagnetic force, but the fusion releases the energy of the strong force. The energy released per nucleon is about 7 times greater in fusion than in fission. Students, in a previous lesson, we looked briefly at what happens when deuterium and tritium, two isotopes of hydrogen, undergo fusion. We determined that they produce helium, a free neutron, and a significant amount of energy. In fact, you now know that such a reaction would produce an incredible amount of energy. This kind of reaction is referred to as a thermonuclear reaction. It is what powers the stars and the sun. If nuclear fusion is capable of producing so much more energy than nuclear fission, why are we not using it today to provide power and energy? Students, can you come up with reasons why nuclear fusion is not a practical energy source? Please get together with a classmate and discuss your ideas.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I wonder what reasons you came up with. The main reason why controlled nuclear fusion is not yet a viable energy source is because it requires an almost impossible amount of energy and pressure in order to occur. In fact, it requires a temperature equal to the internal temperature of the sun. Here we see a depiction of the fusion of deuterium and tritium. The nuclei, both positively charged, naturally repel one another. As temperature increases, so does the kinetic energy of each nucleus. Each nucleus moves randomly at progressively higher speeds. When the temperature reaches many millions of degrees Kelvin, the kinetic energy of the nuclei overcomes their force of repulsion, and the two collide. The collision of tritium and deuterium yields a helium nucleus and a free neutron. It releases tremendous energy in the form of heat. Students, I hope that you found today's lesson as interesting as I did. You have learned the difference between nuclear fission and nuclear fusion. You have studied how each reaction produces energy, and you can explain why nuclear fusion is not yet a practical source of energy. Until next time, thank you, teacher. Thank you, students.